All right, so we'll move into chapter 6 here, okay? And we will do confidence intervals. All right, but let's just go back to what we covered right before the break, in that in chapter 5, we covered sampling distributions. And in particular, we covered the central limit theorem. All right. So, does anyone feel confident enough to summarize what the central limit theorem states? You can flip back in your notes. That's fine. And maybe I didn't do a good enough job covering it then. Okay, so we'll just flip back 2 slides.
Oh, it's...
Yeah, go ahead.
So it's, I mean, simply it's like, it's just the distribution of all means from several samples.
Yes, so that's a sampling distribution. That's the sampling distribution.
Oh,
yeah.
sorry.
And the central limit theorem is that the sampling distribution, as long as these conditions are met, will follow the normal distribution. Okay? So we're saying if we generate a sampling distribution, meaning we repeatedly take different y bars from a population, or repeatedly take samples from a population and create y bars for each sample, the distribution of y bars, that sampling distribution, will follow the normal distribution with this mean and standard deviation. That's what the central limit theorem states, okay? Basically, in short, is that a sampling distribution of y bar will follow the normal distribution. With a little asterisk, meaning there are certain conditions that apply for that to be the case. But that's essentially what the central limit theorem states. Okay? You create the sampling distribution, which is the distribution of basically all possible y bars that can come from different samples. That thing will follow the normal distribution. Okay, so keep that in mind. Keep that in mind. All right, so let's go get into the idea behind a confidence intervals. Okay, so in chapter 5 we were talking about the sampling distribution, and we said if the population has these properties, meaning I told you the population had a certain mean and the population had a certain standard deviation. So in chapter 5 we knew the properties or parameters of the population. Okay, we knew mu and the standard deviation sigma. Okay, but in real life this is almost never the case. Okay, generally when we want to study the population, we want to study it because we don't know mu or we don't know sigma or something like that. So in real life, we generally do not know mu or sigma of the population. And so we have to, so chapter 6 is essentially we're going to try to create an estimate of mu, okay? So the population is this big, large entity that we can't observe directly. But from the population, we pull out a little sample, and we study the sample. So let's say from the sample, we observe y bar. Okay, the sample has this mean y bar. What does that say about mu in the population? Okay, y bar say all right, so let's say we went to Europe, okay? So I said in the United States, the average height of women, 64.5 inches, okay? But let's say we went to some other country, whatever, country that we don't know, and we took a random sample, maybe of 30 different women. Somehow we got a random sample of women. We measured how tall they are, and we got the average height to be 65.5 inches. What does that say about the mean height of that population? Is it necessarily? Maybe, right?
How big is the sample? That's what I'm saying.
Let's say 30 people.
Okay.
Okay, so,
So it doesn't tell you.
well, I don't know. Or does it? Does it tell us something or does it not? That's the question. That's the question we're asking, okay? So let's say just example. So for example, I don't know, we discover, there's like this new nation, undiscovered. There's an island in the ocean, inhabited by people. They're friendly, okay? And they speak English and use the customary system nicely, so it works out. But okay, so anyway, we just take a random sample. So this is island nation. All right, random sample of 30 women. Okay, and the mean height of the 30 people, or 30 women, I should say, is 65.5 inches. And we'll just we'll say the sample or the standard deviation of the sample is let's say 3.5 inches. Okay. What does this say about the mu, the mean of the population, the mean height of the entire island's population? Of the populations. Okay. Does it say anything? I would argue no. Well, actually, later on we'll find out that even if the island only had, as long as we're not violating the condition, so the island has at least 300 people, but let's say there's 5,000 people or 30,000 or 1,000,000 people on the island, as long as your sample is selected randomly, that aspect actually doesn't make a huge difference. Okay. All right, so keep that in mind, right? We want to know, what can we say about mu if we know that the mean of our sample is 65.5? Well, there's a few things we can say, right? We know that the mean height's not going to be 20 inches, right? We know that the mean height's not going to be 100 inches. Could the mean height be 60 inches? Maybe. Could it be, 65 inches? That seems more likely. What about 68? So we want to get an idea based on the sample. What can we say about the population? That's what we're essentially trying to do, okay, with a confidence interval. Well, actually, all right. So put this thought on hold, and I'm going to make a analogy or another illustration here. Okay. So let's say somebody takes a picture, posts this photo on Instagram, okay, and all right, so they're on the This is a, this is terrible. It's a doggy. Okay. All right, and so this dog is located, it's on a football field, all right, so, you know, hashtag football field, whatever. Okay, so there's a dog, and then, but it says, where is the invisible owner? And it also says invisible leash. This is so terrible. Okay, so here's a picture. Okay, there's a photograph of a dog. All right, and the idea is the dog is going for a walk. When we took this photograph, the dog is located at the 30-yard line. Okay, but there is an invisible owner with an invisible leash, and we want to know, well, where's the owner? Do we know where the owner is? Okay. We don't, but I will provide you some info, okay? So we'll say we know a little bit about the dog and the leash. So we're asking, where is the invisible owner? That's what we want to know. Okay, so we know a bit about the dog and leash. The dog is usually well behaved, doesn't like to pull very hard against the leash. And the leash is elastic, okay? Leash is elastic. And dog generally does not like to pull very hard against the leash. Okay. In fact, 68% of the time, the dog remains within 1 yard of the owner. Okay, and 95% of the time, the dog remains within 2 yards of the owner. Okay, and 99.7% of the time, within 3 yards of the owner. Okay. All right, so based on this, if we see the dog located at the 30-yard line, what can we say about the location of the owner? Well, that the owner
more or less than 3 yards away.
Okay, so, well, is that true? So you guys are saying the owner, if you see the dog at the 30-yard line, the owner is certainly between the 27 and 33-yard lines? 99.7%. Could the owner be at 26.5 yards? More than 3 yards away? It's possible, but that would mean what? This picture was taken at one of those odd moments where the dog decided to go more than 3 yards away from the owner, okay? But we can make little statements like, so we can't be for certain, we can't be certain about where the owner is, okay? You know, he's invisible, right? We can't be certain, but we can say, well, I know that the dog is at the 30-yard line, and I know this about the dog, these behaviors about the dog, so that I can say something like, I am 95% confident that the owner is between 28 and 32 yard lines. Does that make sense? So we can say I'm 95% confident that the owner is between 28 and 32. Could the owner be outside of 28? Yes. But because we know the behavior of the dog, when we see a picture like this, we can be 95% confident that the owner is between 28 and 32. If the owner is outside of 28 and 32, it's possible. That just means the picture was taken in a rather rare moment where the dog was more than 2 yards away from the owner. Okay? Owner, you know.
So would that rare moment be considered an outlier?
Well, it just, so outlier, well, outliers generally are individual data points in the context of a larger data set. So if you just have one isolated event, it's hard to say an outlier, but you could just say it was an odd, unexpected event, I guess you could say. Okay, so the owner could be more than 2 yards from the dog, but that means this photo was taken at an unusual time. Okay, so how does this relate back, or I'll let you guys finish writing all of that. How does this relate back to the original question that I had? Okay, so what we originally said was we've taken a sample of 30 women from the island, and the mean of the sample was 65.5. What does this say about the mu of the population? Okay, in this circumstance, in trying to tie it back to this this example, we can think of y bar as the location of the dog. Okay, and mu is the invisible owner. And the central limit theorem is the combined behavior of dog and leash. Okay, so we want to know the location of mu. We don't know where it is. We don't know where the owner is, invisible owner is. We don't know where the population mean is. What we do see, we can observe y bar. We can observe the mean of a sample, or we can observe the location of the dog. The central limit theorem, which states that y bars come from a normal distribution, meaning 95% of the time it's within 2 standard deviations of the mean, and 99.7 it's within 3 standard deviations of the mean. That behavior, the behavior of y bar, is similar to the behavior of the dog. Does that make sense? So based on this, we can say, based on the central limit theorem, we can make statements like, we can then make, statements like, okay, if y bar is 65.5, then I am 95% confident that mu, the mean of the population, is within 2 standard deviations of 65.5. Is this statement? Huh? Yeah, we're not. We're the dog was to kind of illustrate where we're going, okay? But now we're dealing with sample means and population means. We don't know the mean of the population. We can observe the sample and the sample mean. So based on what we see in the sample mean, what does that say about the mean of the population? And I'm arguing that because of the central limit theorem, because we know that y bar comes from a normal distribution, okay, we can then be confident that if y bar is located here, 65.5 or wherever it is, then that means the mean of the population mu shouldn't be very, very far away from that. Is that okay?
That's still not very accurate, though.
Well, so here, what is this standard deviation, though? Okay, so it's the standard deviation of the sampling distribution. It's not the standard deviation of the sample. Okay, so we'll get into all of that. All right. So we need to fix this up a little bit, and it's technically not 2 standard deviations. It's a little bit different. Okay. So we can say when I say 2 standard deviations, this standard deviation, this is technically, or not technically, it is the standard deviation of the sampling distribution, right? Because y bar, right? So the central limit theorem states that y bar comes from a normal distribution with mean mu and standard deviation sigma over the square root of n. Okay? So this standard deviation is the standard deviation of the sampling distribution, which is sigma over the square root of n. Okay. So we can then make statements like, I am 95% confident that mu is between, and I'm going to write y bar minus 2 sigma over the square root of n, and on the upper end I would have y bar plus 2 times sigma over the square root of n, right? Is the transition into this feeling okay? Or are there questions? Discomfort? I see a look of discomfort, but I want to make sure we're, don't hesitate to ask. So the idea here now is we don't know where mu is. We understand the central limit theorem and sampling distributions, meaning that if we have a population with mean mu, when we take random samples, the y bar comes from a normal distribution centered at mu. So if mu is here, the different y bars we get should be close to it. Sometimes we get something far away, but because it's coming from a normal distribution, we know that around 95% of the time it's not going to be more than 2 standard deviations away from mu. Okay? And the standard deviation being sigma over the square root of n. So if I see y bar over here, then that tells me that the mu should not be more than 2 standard deviations away from y bar. Okay? Even though I don't know where mu is. That's how I'm getting statements like this. I'm 95% confident that mu is between y bar minus 2 standard deviations and y bar plus 2 standard deviations. Does anyone see a bit of a problem here, though?
Oh, we don't know what the standard deviation is.
Yeah, we don't know what the standard deviation is. This presents a bit of a problem, okay? We're saying we don't know what mu is, and that's why we're bothering with this thing. But if we don't know the mean of the population, we're probably not going to know the mean of the standard deviation of the population either, okay? So what should we do? Okay, so let me just flip back a couple slides. So in this situation, we said the mean of our sample was 65.5. We looked at 30 women, and the standard deviation of our sample was 3.5 inches. Okay. Well, I would say the best thing we can do is just take a guess at what the standard deviation of the population is, and just say our best guess for that is going to be the standard deviation of our sample. Okay. We don't know if it's accurate. We don't know if it's too big or too small, but that's probably our best guess right now. Okay, so that's what we're going to do. Okay, so the issue is, but we do not know sigma, okay? So we will use S, the standard deviation of our sample, as our best guess. For sigma. But then that introduces another layer of uncertainty. Okay? So our first layer of uncertainty was that we didn't know what we don't know what mu is, and we're guessing what that is by using y bar, and we're giving ourselves basically this breathing room of plus or minus 2 standard deviations. But we don't even know what the standard deviation is now. Okay? And so to compensate for that, we're not going to use 2 anymore. What do you think we should do? We probably have to use a number bigger or smaller than 2 to compensate for the uncertainty in in sigma. Bigger, right? To give ourselves even more breathing room, okay? Or more room for error. Okay, and this plus or minus, this is known as the margin of error. Okay, so to give ourselves more room for error, we're going to use a number bigger than 2. Okay, and so this is where we bring in something called the t distribution. So let me just let me go back, and we're going to copy this. Okay, so we will now use S in place of sigma, okay? But then we need to adjust this to compensate for the additional uncertainty. Okay, so we're going to adjust this factor of 2. It's also over here and over here. Okay, we're going to adjust this factor of 2 to something else. Okay, And that's where we bring in something called the t-distribution. Okay, and you can look up, it's known as student's t-distribution. And there's an interesting story. The man who developed it, Gossett, was working for Guinness Brewery, but the beer maker in Ireland, and he was in charge of quality control, and he was using basically what he was doing was using or things from the normal distribution at the time, and they were realizing you're rejecting too many beers that are actually pretty good. So he said, well, maybe I need to adjust this to something bigger. And he didn't quite understand the math, so he did an incredible amount of just manual labor to figure out this t-distribution himself. So he developed the t-distribution, basically kind of like this brute force method of taking random samples and calculating standard deviations himself. Rather interesting. But Guinness Brewery didn't want these publications associated with them, so they had this kind of rule that you had to publish under a pseudonym. So Student was the name he chose, and it's a neat little story there. Okay, you can read about it. Well, anyway, okay. So the t-distribution takes into account a few things. Okay, it takes into account your sample size, because if you have a large sample size, the standard deviation from your sample you would expect to be a pretty good estimate of sigma. Okay, so the amount of compensation that needs to be done is not going to be huge. On the other hand, if you have a tiny sample size, like a sample size of 3 or 4, you're probably going to need to make a lot of compensation, because a sample size of 3 or 4 is not going to give you a very accurate estimate of, or not a very precise estimate of sigma. Okay, so the t-distribution takes into account the sample size. Okay, and it's called degrees of freedom. Abbreviated DF. And in this case, it's the sample size n minus 1. Okay, I don't need these parentheses. So DF is n minus 1. Degrees of freedom, it comes, it's the idea of, well, here, I guess this is the maybe easiest way to explain it. We could play a game, and I can say, we're going to pick 10 numbers, and I can make absolutely sure that the average of the 10 numbers is 100. And I can say, you go ahead, you pick 9 numbers. As long as I get to control the 10th number, I can make sure that the average of those 9 numbers is 100. Okay? Does that, and you guys can imagine that, right? Whatever you do, I just have to make sure that everything adds up to 1,000 if we're picking 10 numbers, so that the average is 100. And so in that case, 9 of the numbers, or n minus 1, are free to be whatever they want, but 1 is restricted. Okay, so we have 9 degrees of freedom in that example. And here we're dealing with the sample mean, so that's why we have n minus 1. Okay. So anyway, the t-distribution. It's included in your reference table packet that I passed out. So go ahead and open that up. And it's, I think, the 3rd page. And you'll see on the left-hand column, we've got degrees of freedom. And at the very bottom, you have different confidence levels. Okay? So if you're going to create a 95% confidence level, and we have a sample size of 30, how many degrees of freedom do we have? 29, right? 30 minus 1, n minus 1, we would have 29 degrees of freedom. And so the number that we would use isn't 2, but it's 2.045 according to our table. Okay, and you can see that as the degrees of freedom goes down, the number that we would use instead of 2 gets bigger and bigger until it's quite large with only 1 or 2 degrees of freedom. And on the other hand, if we use larger samples, the numbers get smaller. Okay, and in fact, the true number is not 2 exactly, it's 1.96, and that comes from our normal distribution. So it's, we always say within 2 standard deviations, but it's technically within 1.96 standard deviations according to the normal distribution. 2 is fine, but when we do the t-distribution, we see that the number we use is not 2, but 2.045. So we have just a little bit of a fudge factor. Okay. So anyway, so our revised confidence interval, okay, so our confidence interval is then y bar plus or minus, and I'm going to call it t star times s over the square root of n. So taking everything into account, replacing sigma with s and replacing 2 with a value coming from the t table, and that's what t star represents, we have this. And I've combined the plus side and the minus side into just one thing with the plus and minus. How does that feel? Okay? All right, so let's take a look at our example that we started off with. So, for example, we took a random sample of 30 women from our newly discovered island nation. The mean height of these 30 women was 65.5, and the standard deviation is 3.5. What does this say about mu of the population? Okay, so what we want to do is let's make a 95% confidence interval for mu. Okay, so our data, the bits of data that we have, is that n is equal to 30, y bar is equal to 65.5, and s is equal to 3.5. Formula for confidence interval is y bar plus or minus t star times s over the square root of n. So I'm going to have 65.5 plus or minus, and we look up t star for 95% confidence and degrees of freedom equal to 29 is equal to, I think, what did I say? 2.045. So this is what I have, and so this becomes 65.5 plus or minus, and I'm going to just multiply all of this over here. 3.5 divided by the square root of 30 times 2.045. 1.306. I'm just going to round off to 1.3. Okay? So I have 65.5 plus or minus 1.3, which gives me 66.8 on the high end, and 65 minus 1.3 would be 64.2 to 66.8. Alright, so then I would make a statement. I am 95% confident that the mean height of all the women on the island is between 64.2 inches and 66.8 inches. Okay, mean height of all the women being the mu of the population, right? We always make a statement about the mean of the population. Is this interpretation comfortable with you guys? Okay. How do we get here? We are creating an interval based on our sample mean because our understanding of the central limit theorem says that y bars come from the normal distribution, or in other words, y bars should be close to mu. All right. So let me copy this right here. All right, so this is an appropriate interpretation of our confidence interval. I'm just going to move this over into this corner over here. Yeah. Let's just cut that. Okay, so there are some incorrect interpretations. Okay, so let me just write this. Correct interpretation to say I am 95% confident that mu is between blank and blank. In this case, 64.2 and 66.8, right? But of course, depending on your problem, it's going to be something else. Wrong, let's say, would be to say I am 95% confident that y bar, which is the sample mean, is between blank and blank. Why is this wrong? Yeah. Huh? We know the sample mean, right? We know the sample mean. Okay? It's meaningless to assign a value of confidence to the sample mean. Okay, we're 100% certain that the sample mean is this, because we know the sample mean. Okay, we know the sample mean. All right. Wrong. I'm 95% confident that future values, meaning future values will be between blank and blank. Or going along with that, 95% confident that, or you know, it's also wrong to say 95% of women on the island have heights between blank and blank. Okay. Both of these are wrong because our confidence interval is about mu. It's not about individuals. Okay. Individuals can have a wide spread. Individuals can have, you know, there could be women who are 6 feet tall and, you know, things like that. But the mean of the population, this is the only thing we're making a statement about. Okay, we're only making a statement about the mean of the population, not about individuals. I'm sorry, we are not making a statement about individuals. Okay, we make statements about mu. Okay, other wrong interpretations. It is not correct to say there is a 95% probability that mu is between blank and blank. All right, what's wrong with this statement? Why do I have to say confident? Why do I have to say I'm 95% confident and not to say there's a 95% probability that mu is between blank and blank? Probability. Yeah, well, probability. Okay, well, here, let's talk about this. Let me see if I can find a coin here. All right, so I have a coin. I've got a dime. All right, and let's see if I can catch this. No, I can't. Okay. Well, all right. So I'm going to flip this, and I'm going to ask, you know, what is the probability that this coin will land on heads? And your answer is 50%, right? 0.5. Okay. So I flipped it. All right. And I'm going to ask you this question now. What is the probability that the coin landed heads? Okay, you guys are still saying 50%. All right. All right. And then now I'm going to say this. So I'm looking at the coin. And I'm going to ask you the same question. What is the probability that the coin landed heads? Okay, so some of you guys are still saying 0.5. But yeah, now it feels a little funny, right? Because now you know that I looked at it. Well, the thing is probability, if we think about the definition of probability, probability only makes sense in the context of uncertain events. Okay, so it made sense to ask what is the probability that the coin will land heads before I flipped it. Okay, however, after I flipped it, it doesn't make sense to ask what is the probability that this happened, because it either happened or it didn't. There's no more uncertainty. The event has been determined. Okay, there's no uncertainty here. So you don't know how the coin landed, okay? But it would be incorrect for you to say there is a 50% probability that the coin landed heads. It would be correct for you to say I am 50% confident that the coin landed heads, but it's not correct for you to make a statement of probability about the coin landing heads. Does that make sense? Okay, at least in our frequentist interpretation of probability. Okay, so it only makes sense to talk about probability if there are uncertain events. Once an event is determined, there's no probability associated with it. If you don't know what it is, you can only talk about confidence. So in this case, the value mu is a fixed value of the population. It's a property of the population. There's no uncertainty in mu. it doesn't make sense to assign a probability to that. Mu is either going to be between these two values or it's not. There's no uncertainty there. So it doesn't make sense to talk about probability. We can only talk about the confidence, our confidence in knowing where it lies. Okay, so probability only applies uncertain events. Okay, mu is a fixed property or parameter of the population. There is no uncertainty. Okay. So it does not make sense to talk about probability. So we have to talk about confidence. If you do Bayesian statistics where everything is now a belief, then you can talk about probabilities they're called probability intervals. But that's the other interpretation of probability, and we're taking the classical frequentist view here. Okay, coin-landed heads if you care. And so, just make sure you know the correct interpretation for a confidence interval. Okay, so let's just try a simple example. So let's say we take a random sample of, all right, so we'll take a random sample of, we'll say 25 men on the island. Okay, the average height of men average height of these 25 men is 72 inches with a standard deviation of 2.5 inches. Okay, make a 95% confidence interval for the mean height of all men on the island. Okay, so go ahead and work through that. How are we doing? Are we able to get started? All right, so we went ahead and worked through it. This is our equation for a confidence interval. Our data says that the mean of our sample is 72, the standard deviation of our sample is 2.5, the size of our sample is 25 men. We will have n minus 1 or 24 degrees of freedom, and we're making a 95% confidence interval. So the t-star that we use, looking that up in the table, is 2.064. Maybe I'll note that if you cannot find the exact degrees of freedom in the table, round down. Okay, so if you have, you know, what's in the table? If you have a sample size of 77, you would have 76 degrees of freedom. You won't find the row 76 degrees of freedom in your table. So in that case, round down, and you do find 70 degrees of freedom. Okay. If you have a computer, it's not a big deal because it'll have all the degrees of freedom built in. But if you're using a table and doing this thing manually, if you can't find degrees of freedom, round.
It's like 79. Should round out to 79.
Yeah, round down. Okay. It's just as like a safety factor, because going the other direction, you might use a t-star that's too small. But I mean, it's probably not going to make a huge difference if you do it wrong. But the correct thing to do would be to round down. Okay, so anyway, you look that up, you get 2.064 as your t-star, and so we just plug that in, and I get 72 plus or minus 1.032. So that leads me to two numbers, 73.032 and 70.968. If you want to round those off, you can, but I just left them in this full form. And I am 95, thus my thing becomes, I am 95% confident that the mean height of all men on the island is between 70.968 inches and 73.032 inches. Okay. If I tell you, let's say in the USA, the mean height of men is 69.5 inches. Okay. What do we have evidence that the mean height of men on the island is different from the mean height of men in the US? Sample size is 25 men. What do you guys think? Some of you are shaking your head. So those of you who are saying no, what do you say no?
We only have 95% confidence that it's different, but we don't have evidence that it's different. We haven't reached like certainty.
Yeah, well, okay, what is certainty?
If we've taken all of the people, all the men on the island.
Okay, so, but that was not the question. It says, do we have evidence? Okay, so yeah, the question is, do we know, if the question was, do we know for certain that the mean height of men on the island is different from the mean height of men in the US? The answer to that is no, we do not know for certain. And the only way to know for certain is to measure all men on the island and get a true value for the island. And we technically also need to measure all men in the US to get a true value for the US. And then we would see, are they exactly the same or are they different? and then we can answer that question. All right. But here, you know, we only looked at 25 men, but based on our confidence interval, I mean, basically goes from 71 to 73 inches, right? If I'm just rounding off to the whole number, basically goes from 71 to 73 inches. Okay, that is evidence. Okay, we only looked at 25 men, but the sample of the 25 men that we looked at on the island had a mean of 72 inches, which is different enough that our confidence interval does not include this number 69.5. Okay, so 69.5, which is the mean height of men in the U.S., is outside of our confidence interval. Even if it was 70, or even if it was 70.8, that's outside of our confidence interval, which goes from 70.968 to 73.032. So we do have evidence that the mean height of men on the island is different from the mean height of men in the U.S. Okay, even though it's only 25 data points.
So
Yes.
if it was inclusive of that value, then we wouldn't have it.
Then we would not have
So if it
evidence.
was in there.
Yeah. So I'll write that down, and then we'll flip back 2 slides and look at the example with the women. Okay. So so I'll say the confidence interval for the mean height of men on the island does not include 69.5. Thus, we have evidence that the mu, or the mean height of the men on the island is different from the mu of men in the USA. Okay, because 69.5 is not within the interval. So I'll let you guys write that down. I'm going to flip back 2 slides here. All right, and so this was the confidence interval that we made for women on the island, okay? So this was the confidence interval we made for women on the island, and we stated that in the USA, mean height of women is 64.5 inches. Okay? So in this case, 64.5 is between the ends of the interval. So we would write 64.5 is contained within the interval for the mean height of women on the island. Okay, so we do not have evidence that the mean height of women mean height of women, I should say, on the island is different And so here is the, I guess, contrasting conclusion, in that if the value that you want to know about is within the interval, then you do not have evidence that it's different. Okay? Does this mean that the mean height of women on the island is the same as the mean height of women in the US? No, it doesn't mean that. It's just that we looked at 30 women. That's not enough for us to come to the conclusion that it's different from the mean height in the US. Okay, so it's not evidence that it's the same. It's just not enough evidence to say that it's different. Okay, so I should say, do not say that. Do not say that the mean heights of women on the island is the same as it is for the USA. Okay? We do not have evidence that it's different. But this is not evidence but it's not evidence that they are the same either. Okay? All right. How's this feeling? Okay? So again, our confidence intervals are based on the central limit theorem and our understanding that sample means y bar come from a normal distribution centered around mu. Okay? Remember, there were conditions for the central limit theorem to apply. Okay? And so because the confidence intervals, the conclusions from a confidence interval depend on the central limit theorem being true, the same conditions that are required to make the central limit theorem true need to be true for a confidence interval. Okay? So confidence intervals depend on the central limit theorem. So the conditions for the CLT to be true must be met in order for the conclusions of the CI to be true. Oh, before I forget, let me just write in the corner different confidence levels. Note to myself. Okay? So if you just recall those conditions that must be met. Okay? The sample must be selected randomly. And individuals independently. Okay. Sample not too big. Less than 10% of population. And also sample not too small. Okay? Rule of thumb, at least n equal to 30, or the population is normal. So these conditions, same for the central limit theorem, must be true in order for us to have valid conclusions from a confidence interval. Okay, so that, statistics is a great subject, and it can help us answer questions and things like that. But a lot of times there are conditions or assumptions that must be met, and so if these conditions aren't met and you just take data and just pretend like they are met and they're not met, you might come to conclusions, you might have numbers and things like that, and you might feel like you're doing good work, but your conclusions are probably going to be wildly off, especially if the data wasn't collected in a random manner, or if a lot of these things don't apply, it can get you in trouble. Okay, and this first one, we always say the sample must be selected randomly and individuals independently, and at all of our examples we just say the sample was selected randomly. That's a very it's actually a very difficult condition to be met. Okay, so anytime you take a poll, news organizations do polling and things like that, and they're basing conclusions and predicting election results based on these polls. If their polling methods for selecting people are flawed, the conclusions you're going to draw are going to be flawed as well. Okay, all right, so the last thing, I forgot to cover this earlier. So different confidence levels. How would a 99% confidence interval compare to a 95% confidence interval? What do you think? Wider, narrower, or depends on the situation? So assuming we're using the same data, and the only thing we did was, instead of a 95% confidence interval, we're going to make a 99% confidence interval. Okay, so same data, just changing the confidence. What do you guys think? It's going to be wider. Okay, so if we want to be more confident, it's going to be wider. Okay, so let's just think about this. Okay, so just imagine, we can think about the dog and the invisible owner, right? We could be 95% confident that the owner is between the 28 and 32 yard line. Okay, if we wanted to be 99% confident, we would say the owner's between what? 27 and 33. Or if we want to be 100% confident, we would just say the owner's, within 100 yards of the dog, or something like that. Okay, so in any of these things, if we want to be more confident that our interval contains the value mu, we just make our interval really wide. Okay, then we can be confident that mu is within the interval. It's just now, but really wide intervals are not very useful to us. Okay, I can say I'm 100% confident that the average income in the United States is between $0 and $1 billion per year. Okay, I'm 100% confident that that's true, but it's not a very useful statement. Okay, because pretty much, yeah, not every income, but certainly the average income in the U.S. is between $0 and $1 billion. Okay, but it would be much more useful to say, well, I'm 90% confident that the average income is between, I don't know, 40,000 and 60,000 or something like that, And I really don't know, but it's probably something like that. So, we have to trade off confidence to create a more narrow interval. Okay, so higher confidence. So if we want to be confident that our interval has the number, we have to create a wide interval. So higher confidence leads to wider intervals. Lower confidence leads to narrower intervals. So you can think of it as, you know, let's say a fugitive escaped, and the police figured he ran into a certain neighborhood. Okay, and so they're going to create a search zone. If they want to be absolutely certain that they find the criminal, they can create a giant search zone. But it's going to take a lot of resources and to comb the entire search zone. So they can decrease their confidence and create a smaller, more manageable search zone at the risk that the criminal is not within the search zone. Okay. So, like in the, this is already a couple of years, or a year, I don't know, Boston Marathon bombings, the guy was hiding in a boat, just, you know, a block outside of the search zone, right? They created a search zone, but it was just not big enough to actually have the fugitive, right? So that happens, okay? So increasing or decreasing confidence, leaving everything else the same, will change the width of the interval. And the only thing that really is affected when we change the interval in this thing, y bar plus or minus t star s over the square root of n, the only thing that changes, this is the only thing that changes. Only part that changes. When changing confidence. Okay, so that's all I've got for today in Chapter 6. There's a few more sections in Chapter 6, but we'll cover that next week. Okay, we've got a midterm exam in 2 weeks. So, and next week you have a quiz. Okay, and so the details of the quiz are covered on the homework page, and and that's it. Yes. Okay.